Imagine a star spinning so rapidly that it starts to challenge the very laws of physics we've come to understand. Sounds like something out of science fiction, right? But it's not. Astronomers have discovered such a celestial body, an ultra-fast spinning star that seems to defy everything we know about gravity, centrifugal force, and stellar mechanics. In today's journey through the cosmos, we'll explore how this incredible star works, what makes it so extraordinary, and what it means for our understanding of physics. Let's begin by breaking down what we know about stars and rotation. Stars are massive balls of gas, mostly hydrogen and helium, held together by their own gravity. Most stars rotate, and some rotate faster than others. Rotation is influenced by a star's formation, its magnetic fields, its mass, and its age. Typically, larger and younger stars rotate faster. But there's a limit to how fast a star can spin before it literally starts to tear itself apart. This boundary is called the breakup speed. It's the point at which centrifugal force from the spinning motion overcomes the star's own gravity. If a star spins faster than this, it would start flinging material into space and could even disintegrate. So when scientists find a star rotating dangerously close to that limit, or possibly beyond it, it's a big deal. That brings us to the star in question. Recently, astronomers detected a star that is spinning at an astonishing speed, so fast that it's close to or possibly exceeding the theoretical breakup point. We're talking about a rotation period of just over 1 millisecond. That means it completes a full rotation more than 700 times in a single second. To put that into perspective, if Earth spun that fast, a day would last less than a second. This spinning marvel is known as a pulsar. Pulsars are a type of neutron star, extremely dense remnants of massive stars that have undergone a supernova explosion. When such a star collapses, its core becomes so dense that protons and electrons merge into neutrons, forming a neutron star. These stars are incredibly small, just about 20 kilometers in diameter, but contain more mass than our sun. Now imagine compressing all that mass into such a tiny space and spinning it at hundreds of revolutions per second. That's what we're dealing with here. So, how is it even possible for something like this to exist without violating physics? Well, this is where things get really interesting. Some theories suggest that extreme magnetic fields, known as magnetars, can help stabilize the star. Others believe that the laws of physics as we understand them may not fully apply under such extreme conditions. It opens up the possibility that new physics may be required to explain what we're observing. One explanation that scientists are exploring is the role of centrifugal forces and how they interact with the dense core of a neutron star. As the star spins faster, the outer layers may bulge at the equator, creating a flattened shape known as an oblate spheroid. This redistribution of mass can allow the star to spin faster than expected, but only up to a certain point. Beyond that, the internal structure of the star must adapt, or break. Another possibility involves the star's internal composition. If it's made of exotic matter, like quark-gluon plasma, it may be more resistant to breakup forces. This would mean we're looking at a state of matter not typically found in the universe and only produced under the most extreme gravitational and thermal conditions. There's also the idea of accretion. In binary star systems, one star can siphon material from its companion. This inflow of matter adds angular momentum, spinning up the neutron star like a cosmic carousel. This process could explain how the star got to such extreme rotation speeds, but it still doesn't fully answer how it remains stable. Now, let's talk about the implications. First, it challenges the boundaries of known astrophysics. If stars can spin faster than what theory predicts, then either our understanding of gravity, pressure, or centrifugal limits is incomplete. This could lead to revisions in the equations that define stellar dynamics and rotational physics. Second, it has applications in gravitational wave research. Extremely fast-spinning neutron stars can emit ripples in space-time, known as gravitational waves, especially if they have asymmetrical mass distributions. By studying these stars, we might gain deeper insight into these elusive cosmic signals. Third, it could redefine what we know about the life cycle of stars. Neutron stars are usually thought of as dead ends, final remnants of massive stars, but this discovery shows they may still evolve, gain mass, or even break apart if pushed to their limits. This discovery also reminds us of how dynamic and strange the universe truly is. Just when we think we have the rules figured out, a celestial object comes along and throws a wrench into our understanding.